Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome, as I already indicated. Today we're going to focus on electricity. I know that you have covered electricity, so we're going to make sure now that we deal with the issue of internal resistance. Remember, as you were writing your exams, you didn't have internal resistance. Now we're going to have internal resistance included in our calculations. I hope this will help you as we prepare for your exams. Remember, we're still in paper 1, and we're saying for paper 1, we have mechanics with 65 marks. We have wave, sound, and light, which is your Doppler effect, with 15 marks. We have electricity and magnetism with 55 marks. So you can see we have a lot of marks from this knowledge area, electricity and magnetism. Then we have metal and materials, which is your photoelectric effect with 15 marks. The total for paper 1 is 150 marks, and you will be writing for 3 hours. And then those are the cognitive levels that you will be assessed on. So I'm hoping that you will be able to understand and move with me, and I will be giving you exam skills so that you prepare and you are ready to deal with electricity questions. Remember our structure of our paper, we're saying we still have 10 multiple choice questions with 20 marks, and we're having 130 marks, which are your structured questions. The total for the paper is still 150 marks and 3 hours. This will be so for your final exams as well as for your prelim. I know that wherever you are worried about the preliminary examination, so it's important that we always talk to that. You have covered this topic, and then if you look at your ATP, you were required to state Ohm's law, which is you already by now. I'm hoping that you know how to state Ohm's law, so we'll do that, which easily said. We are saying, remember, it's about the potential difference across the conductor. So you will say the potential difference across the conductor is directly proportional. So you can just say the potential difference across the conductor is directly proportional to the current, provided the temperature remains constant. So the main thing is that our resistors must not be too hot, otherwise we won't be able to obey Ohm's law. In order for us to obey Ohm's law, we're saying the temperature must remain constant. So we're saying the potential difference across the conductor is directly proportional to the current, provided. So this is very much important to say. This will V is directly proportional to I only when the temperature remains constant. Immediately when the temperature is not remaining constant, it means now we cannot be able to obey Ohm's law. So this is coming from, when you rearrange your Ohm's law equation, we'll get V equals to IR. And then if we are saying the temperature of the resistor remains constant, we are remaining with V and I, which are the two variables there that we're talking about, to say as the potential difference increases, the current will increase as well. Then provided the temperature is remaining the same. So it's very much important that as you prepare yourself, you know how to state Ohm's law. You must be able to interpret graphs and data as well. So you'll be given information. You must be able to do that. We must be able to identify the ohmic and the non-ohmic conductors, to see the difference between the ohmic and the non-ohmic conductors. As I've indicated already, that ohmic conductor, it will obey Ohm's law, which means that is when the temperature remains constant, then we obey Ohm's law. That's, we talk about ohmic conductor, it obeys Ohm's law, but the non-ohmic conductor does not obey Ohm's law. And we must be able as well to use the R equals to V over I, and then we are saying for circuits containing resistors that are connected in series and in parallel. We do maximum of 4 resistors, so we can have 2 in series and the other 2 in parallel, or the combination, or only in series, and all that you'll see as we do our activity. So it's very much important that you practice as many scenarios as possible. The other thing which is important is power. You must be able to know. I know that you have done under mechanics, you have done work, energy, and power. You still do power and energy here. You will be asking yourself, why don't we talk about work? Because if you look at these equations, they are all showing you work there. What is happening there? We're saying work done is energy transferred. So we still, when we talk about energy, we're still talking about the work done. So it's very much important. Hence, we focus on power and energy, because when you say energy, we're talking about the energy transferred, which is our work done as well. So it's very much important that you always think about that. then you don't have a problem. Remember, in terms of our equations, we're saying that for power is the rate at which work is done. The rate at which work is done, which is given by that equation. And as well, you can say is the rate at which energy is transferred, because we're saying work done is energy transferred. So I want to emphasize that so that you don't forget that when we talk about energy, we're talking about the work done. And then we have other equations like P equals to VI, P equals to I squared R, P equals to V squared R. It's very much important that you do like that. And if you look at how this content is structured, we're trying to show you that the first thing that you look at when you deal with concepts, you will first deal with a definition. When you are having a definition, you must now be able to have your data sheet, and the definition is coming from the exam guideline. So those are two documents that we are always encouraging you to say, these are your friends. They must be close to you at all times. You must have your exam guideline. That's where you will get your correct definitions. You must have your data sheet. That's where you will get the correct formulas. And we're saying, as you use these formulas, you must be able to copy them as they appear in the data sheet. Then you can be able to substitute after that. Only then you can be able to calculate what the variables that you are looking for. Now, our main focus, which is now internal resistance, we are saying you must be able to explain the term internal resistance, and you must be able to solve circuit problems using the equation E equals to, just want to write it here, E equals to IR. I prefer to start with the IR for the internal resistance. So if we look, we'll be having our EMF, and then we'll be having our current that is flowing, which is the total current that is flowing in the circuit. You'll having this small r, which is our internal resistance. So you've got to be able to see that that r stands for internal resistance, and the capital one is the resistance, effective resistance. Now you must be able to solve problems using those that equation, and you must be able to solve problems with internal resistance for circuit containing arrangements of resistors in series and in parallel. So we'll have both series and parallel. So I'll spend some time as well indicating to yourself the difference between series and parallel connection when it comes to current and potential difference, so that this question you can enjoy them. Now let's look at these two concepts, which is potential difference and EMF. I find learners, they still have a problem with defining EMF, for example. They still find that definition difficult. But I know it's not about you. It won't be difficult for you because we are dealing with it. We're coming with ways to say, how do I remember how to define EMF and how to define a potential difference? You will remember in grade 10 and 11, more especially in grade 10, you have defined potential difference as the work done to move a charge from one point to another, which is work per unit charge, which is W over Q. Remember, we said the work done is the energy transferred. So hence, when we define the EMF, we still have the same concept, but now because we're talking about EMF, now we're talking about the maximum energy transferred. So the difference is that now the work done there is a maximum. So it's maximum energy per unit charge of a coulomb. So it's a maximum energy per unit charge of a coulomb. So that is the only thing that is differentiating there. But the rest of the definition, you can see that they talk to the same thing. So it's very much important that you understand that if you understand what is potential difference, it will be very difficult for you not to understand how to define the EMF, because now we're talking about the maximum energy transferred per unit charge of a coulomb. So it's very much important that you always at all times remember that the difference there is that with the EMF, we're talking about maximum, we're talking about the whole of it, and then we'll be able to demonstrate that, and I hope that is going to help you as we move on with this type of questions. Now, this Volt that we're talking about is after Alessandro Volt. I just wanted to give you a little bit of history to say they lived between 1745 and 1827. It's important because we encourage you as well, those who will be following streams of research and scientific research and all that. We are saying you can be able to do research based on the electricity as well, and then we are hoping that you will do and find even more other things which are different. And then he lived in 1800. it developed what is known as voltaic pile, which is produced a steady flow of electric current. This formed the basis of the modern electric battery. So the battery that we're using, hence we're referring to the voltage now as volt, from his name Alessandro Volta, who is the one who discovered all that. So you see the styles that we are using these days. From his experiments, Volta discovered that the most effective pair of metals to be zinc and silver, between which was placed card soaked in brine. The brine acted as an electrolyte. You will be dealing with the electrolyte a lot in this term, as you will be doing your electrochemistry, and then it applies even here. We're saying inside this cell, we're having those electrolytes now, which is your solution there that is soaked there inside that cell, and it will allow the charges to pass. Remember, it's about the positive charge and the negative charge. Hence, when you get your cell, it's a return positive there and negative. So you can see we are saying we have a high concentration of negative charges here, and then we have high concentration of positive charge. And when the two mix up now, we are saying the battery becomes flat. It just means that we no longer have that polarity, the difference in terms of the positive charges and the negative charges. So it's very much important that you understand. So strictly speaking, these are not batteries. You can't refer to this as a battery. You will refer to it as a cell. Remember, it only talk about a battery when it's two or more cells joined together. I think your grade 8, 9, 10 syllabus have told you that. Then you understand the difference between a battery and a cell. When it's alone, we are saying it's a cell, but when we join the two or more joined together, we refer to them as a battery, just to bring back your basics so that we are able to move together. Now, you must be able to understand, write down the names of the following circuit symbols, because we want to focus as well on the circuit. Because one thing that I want to emphasize on this lesson is to say that spend time understanding the circuit diagram. Don't rush to go to the question. Remember, the questions are based on the diagram. You won't be able to answer questions if you don't understand the circuit diagram. Hence, we'll be emphasizing the circuit diagram so that when you go to the questions already, you know what you're going to do, because the circuit diagram has all your solutions for the problem. So we're going to spend some time dealing with circuit diagrams and ensuring that you understand the circuit diagram, and we won't have a problem. Let's look now at those symbols. As simple as they look, you have that symbol which you will know that is your cell. And if you look at the issue of the connection, to say cells can be connected in series and in parallel. However, you will see that in all the questions, that most of the questions that we are asking you, we have the cells connected in series. So you have the resistor there, and then your resistors, we are saying these resistors, they can be connected in series. And then in series, you'll know that one after another. You know, when you are saying, I'm watching a series, you watch a series today, you still watch it tomorrow, one after the other. In the same fashion, we are saying the resistors are in series when they are connected in that order. But now, when you say resistors in parallel, now we'll be saying now these resistors, they are connected in parallel. For example, if I draw that, those two will be in series. I draw the other two, and then we can be able to connect them like that. And then if I draw like that, then I can be able to put a cell there. Then you're able to say these cells are connected in parallel. So parallel connection, all of them, you can see they're drawing their currents. They are drawing their current from those 2 points there, these 2 points there. Then you can see that they are all in parallel, but the twos are in series. However, for our studies, we are saying you can only do 4 resistors, not more than 4 resistors. Now we have a switch there. You can't refer to it as a switch because it's either an open switch or a closed switch. So if it's like that, we're saying it's an open switch. So it's very much important, because when the switch is open, we are saying now charges can now flow, because the circuit is no longer incomplete, the circuit is complete. But when it's open, we say the circuit is incomplete. So if we are having a battery connected or a cell connected, we will read across the battery, will read the EMF. However, we can close the switch now. You will see most of the time, you will see even in our activities that we're going to do, you will have the switch that is closed, which it symbolizes that when you close the switch, now the current now can flow, the charges can flow, and then the EMF now is going now to be divided into 2. So remember, when the switch is open, we're saying no, when we have the EMF of a battery or EMF of a cell, will just read it across the battery there, because there's no flow of charges because the circuit is incomplete. But immediately when you close the switch, we're saying now the charges start to flow, and when the charges are flowing, the EMF, I don't want you to think that EMF disappears. No, the EMF is now divided into two. It's divided into V internal plus V external. So you are saying now there will be some voltage that will be left inside the cell, hence we refer to it, or inside the battery, hence we refer to it as V internal. And then we'll have some of the voltage which now will go outside of the battery, though that will be called V external. So in real essence, we are saying that when you close the switch, the EMF, if we have internal resistance, remember there will be some questions that will say internal resistance is negligible, meaning that it's too small for you to account for it. So leave it, behave as if there is no internal resistance. We are acknowledging that there is internal resistance, but it's very small. That's for you to be worried about it. Hence, we are saying internal resistance is negligible, so it's too small. So when you say it's internal resistance negligible, we are saying EMF is the same as potential difference when the switch is closed. Remember, when you close the switch, it means now the potential difference and the EMF will have the same amount. So it's very much important for you to understand, to say EMF, when we don't have internal resistance, the EMF will be the same as the potential difference. But when we have internal resistance, the EMF will be divided into V internal plus V external. And when we add these two, they must be able to give you the total energy supplied by the battery per unit charge of a kiloohm, as we define our EMF. So V internal plus V external, we're saying they give us the EMF. But we are saying this happens when we have internal resistance, which I indicated, or is that small letter R. It symbolizes internal resistance plus the IR. The capital R is the R effective, the one that is external. The resistance is the capital R. So you must be able to differentiate between those two. So V internal plus V external, then that gives us that equation of EMF. I hope you understand now the importance of open switch and closed switch. Remember, I'm referring to the switch that is connected to the battery or to the cell, to say that's what it will mean. Now, this switch is connected in series, so we connect our switch in series, and then we have our ammeter now. A is ammeter. We are measuring current. Remember, in grade 10, you defined current as the rate of flow of charges. You say current is the rate at which the charges are flowing. You're saying how many charges are passing that particular point every second. So it's very much important for you to remember that, okay, we're having our current, which is Q over T, which is the rate at which the charges are flowing. And we are saying now that rate is measured in amperes, and we use an ammeter. So this is an instrument that we use to measure. I know you will be doing, majority of you, experiment on the internal resistance for term 3, and then you will be able to remember that and use that. So you know that the ammeter must be connected in series. So it's important to say this one, we're going to connect it in series. Remember, with the switch, we said our switch can be connected there in the series and in the parallel, depending. You'll see when we talk about the equation. But when it comes to the resistors, we're saying we can connect them in series and in parallel. Now, why do we connect the ammeter in series? We connect it in series because we are saying it has negligible resistance. So its resistance is very small. It still allows the charges to pass. It doesn't hinder the flow of charges. It allows the charges to flow. But now, when we go to the voltmeter has very high resistance. So voltmeter has very high resistance, hence we will always connect the voltmeter in parallel. So voltmeter must be connected in parallel. So what is the voltmeter? And how do we connect the voltmeter? We're saying you connect the voltmeter in parallel. So it's very much important. We said the ammeter is connected in series as well there. Okay, I hope we're moving together. Then we have our bulb there. Our bulb, you can connect your bulbs in series and in parallel. So you can have bulbs connected in series and in parallel. Remember, your bulbs are acting as your resistors. They will be able to resist some flow of charges, hence they will now be able to do that. Now, we move to circuits. Remember, I referred to two types of circuit. I said we have a series circuit, we have a parallel circuit. Don't forget, when we mix the two, we'll have a combination of series and parallel circuit. We have some of the circuits that are a combination. So as you get your circuit, you will check whether the circuit is series or the circuit is parallel. If it's in series, it will be connected as indicated there. So you can see that one is connected after another. You can see all of them there, even our light bulbs connected like that. Then we said this circuit is connected in series. However, if you look at the connection this side, you will see that this is a parallel. It's no longer following that. We connected that, but if you check, all of them are connected at those points, same points there as indicated. Hence, we are saying these two circuits each contain the same electrical components arranged in two different ways. There is more lead needed to complete the parallel circuit than the circuit. So we are saying for parallel circuit, you will even need an extra conductor for you to be able to complete the circuit. So you can do that small part of experiment at school, just do the connection. For series, you will see when you want to connect the same in parallel, you will need an extra conductor so that you can be able to connect and complete all your connections. So it's very much important that you do that. Now, in real life, where do we use this series circuit? We are saying this circuit, it shows two lamps connected in series. You can see they're in series one after another. The current flows through one lamp after another. So remember, the current can only flow when the switch is closed. If you see here, the switch is open. Hence, we are saying when we close the switch, the current will start to flow. I want us to talk and understand one another there. To say, you can see we're having that big line, which is our positive terminal, and our negative is that small one. So all the time, understand. And remember, we're talking about flow of charges in terms of conventional current. So conventional current, we're saying our charges, they flow from the positive to the negative. So the expectation is that the EMF of this battery, the EMF of this battery is going to power the charges across here to flow. So it is the EMF that makes when the switch is closed. The EMF is going to ensure that the charges flow there. And what are we saying? We're saying as the current comes here, it will flow through one lamp. It will come and flow here and come and flow. If it's 2 amperes, for example, your current that is flowing, it will come, the entire 2 amperes will pass there, then the entire 2 amperes will go there. So we'll have the same current that is flowing across there. So you will understand that when we have resistors connected in series, our current is remaining the same. So it's the same current that will be flowing there. Now we're saying the light on Christmas tree, like at home during Christmas, they are often arranged in series. So they are arranged in series. How do you know that? If one lamp goes out, so maybe at home you find that you are having those Christmas trees, and then they just go off after some time. What can be the cause? So we're saying that these lamps go out, all the others go out when one goes out. So we're saying only when one is damaged, the rest is no longer working. So it's very much important to check which one might be damaged so that you can be able to connect and be able to utilize them. So we're saying the brightness of the bulb is affected by the number of lamps. So the number of lamps in the circuit. More expensive sets of light use parallel circuit. So the more the ones that we use at our homes, for example, we're using parallel combination. Just imagine at home, if you're connecting all your bulbs in series, you will have a problem. When one dies, it means the entire house now will be in darkness. So hence we use the parallel combination. So I will indicate here in the next slide the importance of using a parallel connection. This circuit shows 2 lamps connected in parallel. So these ones, they are connected in parallel. And we're saying when it's in parallel, the current will split. Remember what I said there? I said in series combination, I showed you the 2 amperes to say if the total current is 2 amperes, each resistor will receive that current of 2 amperes. But in this case, let's say, for example, we have identical light bulbs there. If we have 2 amperes as our current that is flowing in this, provided the switch is closed. So it's very much important to always look at the switch to say when the switch is open, you know that this when the switch is open, we are saying no, there's no charges that are flowing. We can't measure current because there is no flowing of charges. However, immediately when you close the switch, we are saying our current is flowing. Hence, when it arrives at this point, it's now getting 2 options. We are saying now the current must split because there are 2 rows to follow. So other current will have to go that side, other current will go that side. But if these 2 are identical, it will mean that they will share the current equally, meaning that this will be 1 amperes and that one will be 1 ampere. So it's very much important for you to understand that when resistors or the light bulbs in this case are connected in parallel, they will divide the current. But when they are connected in series, the current will remain the same. So it's very much important. Here you can see that the 2 amperes is going to be divided into 1 ampere. Don't forget, when they reach this point again, the 2 will combine, will still have 2 amperes of current that flows across here. So it's very much important for you to understand that as the current is flowing there, what is going to happen is that when it reaches that point, it will split into 2 because the resistors or the light bulbs are connected in parallel. Hence, we're saying parallel circuit, they will split the current. So don't forget that. I'm emphasizing that. Now we're saying the lights that we use in our homes are arranged in parallel. So like you can see those beautiful lights there, they are arranged in parallel. If one lamp goes out, all the others are unaffected. So it's very much important as well for you to have those basics as a physical science learner who's doing physics in grade 12, to know that when you're doing electricity, that why we're connecting parallel at home. So we're saying if one of these lamps goes out, the rest will remain unaffected. And the brightness of the bulbs is not affected by the number of lamps in the circuit. Remember, as you increase in the series connection, as you increase the number of lamps, the brightness is going to decrease because the resistance is increasing. So as you increase the resistance, then you will see that the brightness will decrease. So I think you will remember the relationship of what I'm talking about, which is your V and your R, the relationship between the current and the R. Remember, as you increase the number of resistors in series, you are increasing the resistance. So immediately when the resistance increases, the current will decrease. I hope you get that. Hence, we are saying the brightness in these ones, all of them, they will not be affected by the number of the lamps. Those are the advantages of connecting our bulbs or our lamps in parallel. So you understand why at home we're connecting like that. Now, let's go and look at the relationship between current and voltage. So we're going to have to revise this and spend time and understand what is it, because the only thing that is going to hinder us from answering questions is if we don't understand what is happening in these circuit diagrams. If you understand the circuit diagrams, I'm telling you, you will enjoy, you will give us total in this question. Now, let's look at this circuit number 1, for example. If you look there, we're having our cell there. Our cell obviously is going to supply the voltage there. Now, what we got to understand is that our journey starts from the positive. We indicated that we are in a journey. We're going to make these charges to travel, to take a journey, a nice journey. And then our charges now, they are flowing from positive. Remember, what is making the charge to flow is the V, is the EMF. Remember what EMF stands for? It's electromotive force, which is the force that is making the charges to move. So the charges will move because of that, and we are saying it's conventional current. So we know our charges will move from positive, moving like that. You can see the journey that our charges. We have our ammeter there. We said the ammeter is an instrument that we use to measure current. So you can see our current is 0.4 amperes. Now, for these discussions, we're going to take our resistors as being identical, meaning that they have the same resistance. Now, as the current comes to this point, you will see that there are now two options that the charges must take. It's either they take this road or that road. So there are two roads to follow there. Which now roads will the charge go? Now, because they are depending on the resistance here, to say how much is the resistance. In this case, I said they are all the same. I can just call them 1R, 1R. So they are all the same resistance. So they won't have much effect. So what will happen is that the charge will divide equally because the resistance is the same. So which means when we have 0,4, we'll have 0,2 amperes here, and we will have another 0,2 amperes there. So you are able to see that okay, our charges are going to be divided, and the division will depend on the resistance. Remember, when you have highest resistance, you will have less charges that will flow to that resistor. So the resistor with the highest resistance will have low current that moves through it. But if they are equal, they will share the current equal. So I hope you are getting it, to say we are moving these charges, and when we move them, when we come there, the current now is going to be divided. The 0,4 amperes is going to be divided into 2. But because the resistance is the same, we'll divide by 2 all of them. Then we're able to get the 0,2 amperes and 0,2 amperes. So you can see that equally we divided our 0,4 amperes. Now, what happens now is that when the charges continue to flow there, they are flowing. Then when they come to this point, we now have 0,2 amperes adding to another 0,2 amperes, meaning that this A will be the same as this A, which means, what are we saying? We're saying it's 0,2 amperes, 0,2 amperes. They flow. When they come to that point, now they become 0,4 amperes again. And then we'll have now this as 0,4 amperes. Please always follow the current, because once you understand what is happening with the current, the question becomes easier for you. But once you don't understand what is happening to the current, then you will have a problem answering the question. So I'm saying always follow the current. We're saying when resistors are connected in parallel, they will divide the current. But now, what happens to the potential difference, or the voltage? The voltage, you will see we're having EMF here across the battery, and then that EMF we're saying is going to divide itself if we have internal resistance. But in this case, we don't have internal resistance. So what is happening is that if this one and this one, they are in parallel, it will mean that the voltage remain the same. So this is what you must do when you get a circuit diagram to be able to answer questions. So, for example, I'm saying if this is 1,5 volts, then this one will have 1,5 volts, this one will have 1,5 volts, because the voltage in parallel remains the same. Now, there are learners who think that maybe we are having now, where's the other 1,5? Remember, the battery is supplying us with 1,5 volts. Now, for that 1,5 volts that is being supplied here, it doesn't mean that now we have 1,5 and 1, we have 3 volts that this circuit now, these light bulbs are sharing the 3 volts now. You might be asking yourself, where is the other 3 coming from? No, we're simply saying that they are getting their voltage from the same source. They are all of them. You can see this one through the connection, they're connected here, and this one is connected here. So all of them are reading the same 1,5 voltage. So don't look at it as if we're having a 1,5 voltage and another one, then you will start to think that it must be 3 volts. No, it's not 3, it's 1,5 volts that all of them are throwing from the same cell that we're having. So that cell is supplying all of them with 1,5 volts until it becomes flat. Remember, when it's flat, it won't be able to function any longer. So understand that the potential difference remains the same when the light bulbs or the resistors are connected in series. So I have emphasized that because when you do questions, you'll just be looking at that to say, okay, we're having a series connection. What does it mean? Then you are able to apply your mind. Let's move. Now, if you look now, we're having a series connection for circuit diagram number 3 and circuit diagram number 4. So you can see that now we're having a series circuit. Now, as I said, you must follow the current. Then you know that if it's 0.1 amperes there, it must be 0.1 amperes there. It must be 0.1 amperes there. It must be 0.1 amperes there. I hope you will practice this and know at all times that as long as they are in series, the current will remain the same. And you continue to follow the current and be able to see how this current is flowing, and then we won't have a problem. You will at all times know that even if we give you a resistance and other stuff, you'll be able to calculate the other variables, and it will be easier for you if you have that understanding. Now, remember what we said in terms of the potential difference. We said, okay, the because there is no internal resistance, we said the EMF is the same as potential difference. Don't always have that in your mind to say, oh, we don't have internal resistance, means that we have potential difference is the same as our EMF. And then that will mean that when you add this 0.5 and 1.0, you'll get the total potential difference. Total potential difference, which is the same as EMF, which is 1.5 volts. So you can see when the resistors are in series, the current remains the same, but they divide the potential difference amongst themselves. So you can see with 1.5, it was divided into 0.5 and 1 volt. But we have 0.1 amperes, it remained the same throughout. So that is how the series behave. So we're saying resistors in series, they are potential dividers. Resistors in series are potential dividers. Potential difference is what is divided there. Now, what happens to the current? Current remains the same. Current is constant. But the parallel one, as you have seen in the previous example that I gave you, when you have current resistors or light bulbs in parallel, they divide the current, then the potential difference remains the same. So, and I have that understanding immediately when you see a circuit diagram, you check whether it's a series or a parallel. If it's series, you know that the current will remain the same, but the potential difference will be divided, which means our potential difference, our total potential difference will be divided across all the resistors. So I hope you are understanding that. And then it's like you are leaving home with 1.5. And as you go through your journey, because we're saying our journey always is from positive to negative, as you move through your journey, you come across resistors, then you are able to pay from that 1.5 to say, depending on the resistance that I'm going to receive, because of this resistance, it will be lower than the resistance in this one. Because when the resistance is lower, you will give less potential difference. So more energy, more work will be done when you have the highest resistance. Hence, here you are giving one volts, which means the resistance is high. Which means when the resistance is high, more energy will be done in order for the charges to be able to move. I hope we are moving together, and you will forever enjoy this circuit diagram. Now, my last example based on how this current is being divided and what is happening. Look at this one as well. We're saying complete the readings on the ammeters and voltmeters in the following circuits. Maybe I can give you a minute just now, and then you just try and look at it and try to complete. So I'll just pause for a minute as you try to complete. You're just indicating how much will be the current. Remember, the resistance, we are saying it remains the same. On the Roman figure 2, the second one there, we are saying that the resistance there, then tell us what is happening. The resistance is the same of those light bulbs. So I will just take a small pause for just a minute, and then I'll be able to come, and then we'll be able to do your solution. Thank you. Thank you. Thank you very much. Welcome back. I hope you were able to solve that problem. You will have seen that because this is a parallel combination, the expectation is that the current is going to be divided. And if the resistors have the same resistance, they will divide equally, meaning that you will have 1,5 amperes and 1,5 amperes. I hope that's how you responded. And when the two now meet here, they're able again to be 1.5 plus 1.5. We're able to get our 3 amperes. And that's what we're expecting you to do when you're solving problems. Deal with the current, deal with the voltage, and then it will be easier as well to deal with the resistance. Now let's look at Roman figure 2 there to say for Roman figure 2 now you are having 6 volt that is in parallel with this one. Remember the internal resistance we said is negligible, which means that our total potential difference is equals to the EMF. So you will know that because they are in parallel, we're saying the potential difference remain the same. So it must be 6 volts. It must be 6 volts. Remember we said there are not two 6 volts here. They're just reading the same 6 volts because they have their point of connection is the same. They are reading that same 6 volts together there. Then they're able to get like that. Then when you answer questions, it will be easier. You'll see now when you start doing activities, you will be able now to immediately see that the potential difference here must remain the same or the current must be divided depending whether it's parallel or connection. I think we emphasized and you are with me. We are moving together. Now, for us to start, we'll start with multiple choice questions to deal with that. Then we'll go to your structured questions. Now we are saying which one of the following combinations correctly represent the physical quantities measured by the respective instruments. So we're saying which measures which. Look, voltmeter. Voltmeter does not measure resistance. You know that voltmeter does not measure resistance, but you know that ammeter measures current. So for number A, you will have seen that it's only one thing that is correct, is that current is ammeter measures current, but resistance is not measured by voltmeter. Let's go to option number B. Option number B, voltmeter measures potential difference, is correct. Ammeter measures current, is correct. So you are able to see that your right answer is B. So we are hoping this is how you will deal with your multiple choice questions. In fact, we are saying when you're dealing with multiple choice questions, just ensure that you look at all the 4 of them, because we are saying we have distractors and we have 2 possible answers. And if you can look at number C, it's saying voltmeter measures potential difference, is correct. Ammeter cannot measure resistance. The same voltmeter cannot measure that one and that one. So you can see number D is very, very much outside. So you see that you are able to choose number B. Even when you leave the exam room, you know 100% that you responded to a multiple choice questions correctly. Which one of the circuits below can be used to measure the current in a conductor X and the potential difference across its ends? Now here you are dealing with the connection in terms of 1.2 to say in this case we are saying that the voltmeter cannot be connected in series. Look at number B. The voltmeter is in series, so we're saying this is wrong because the voltmeter has higher resistance and it won't allow the charges to flow. Hence now when it's in series, you know it's out. So you can tell that number B and D, they are distractors. They cannot be answers. Why? Because we have the voltmeter connected in series. Now let's go to number C. If you look at number C, the voltmeter is connected in series, correct? But now look at the ammeter there. The ammeter is connected in parallel. We don't connect the ammeter in parallel. We connect the ammeter in series because we indicated that the ammeter has very less resistance, so it still allows the charges to pass. So it's not a problem. We must connect it in series. So we are able to choose number A with no doubt to say A is our correct answer. Now the unit of measurement of the rate of flow of charge. You see this question the capital letters there, the rate of flow of charge. I know, just write it in an equation form. You will see that rate means per unit time. I know you have been doing your paper 2, you have been doing rates of reaction, which you define the rate of reaction is the same. The rate means per unit time. It means we are dividing by time. But what are we dividing by time? Rate means per unit time, and then we are saying flow of charge. So we are having a charge per unit time. And if you understand, you will know that that is the definition of current. So the first thing you must do is the current, but the question is saying the unit. So we want the SI unit of current. That's what this question is asking for. So you must be able to say this question is asking for the SI unit of current. And what is the SI unit of current? Current is measured in amperes. And we said the instrument is ammeter, but the SI unit is amperes, is measured in amperes. Hence, number C will be your correct answer. So I'm hoping that you don't lose those keywords like the unit, because the unit, we are saying the SI unit. So we are not looking for current, we are looking for the SI unit of current, in this case, of the rate of flow of charge, which is amperes. I hope we did well in terms of that. Now, in the second diagram, the internal resistance of the battery and the resistance of the connecting wires are negligible. So we're saying there is no internal resistance, meaning that the potential difference that is coming out here is the same as the E. Is the same as our E. So E is the total, and then that E is going to be divided. Remember, we said immediately when we see a series connection, you must know that these are potential dividers. So which means the E must be divided into 2. How do we know how much we're going to divide? We're going to divide based on the amount of resistance. You can see this is R. This is 2R, which means whatever this is 2 times that one. I think we are together in terms of that one. So we're saying the 2 resistors have resistance of R and 2R, and the voltmeter reading across one of them is V. The R1, it gives us V. Obviously now, what is the voltmeter reading across the other resistor? So you will have indicated that if this one is indicating only 1/3 of what is happening, this one is representing 2/3, because when you add 1/3 E plus 2/3 E, they must be able to give you E, which is our total. So we're saying this one is our E, and we're saying here we'll bring 1/3 of E because of the ratios between those, and then here we'll have 2/3 of E, and then the question was about here how much is the voltmeter reading, which is C there. So you're able with no doubt to choose C as your correct answer. Now we move to 1.5, which says the diagram shows the light bulbs X and Y connected in series to a battery with negligible internal resistance. Bulb X glows brighter than bulb Y. Which one of the following is correct? Remember, we said the glowing, in terms of the parallel combination, the glowing remains there, remains the same. But now here we're saying now current in X is less than current in Y. So they're saying we have more current in here. You're saying current is more here, and then they're saying current is less there. Look at that option. The second option, which is number B. Number B is saying to you resistance of X is less. Resistance of X is less than resistance of Y. So that's what they're saying. And you can see already that now the two statements, they are not talking to one another, because if current is low, resistance must be high. But these two is saying current is low and resistance is low. So now we're going to look at those two statements to check which one is correct. But if we look at number C, option number C is saying resistance of X is greater than resistance of Y. So you're able now to say, okay, we have resistance of X, which is greater than resistance of Y. So it's just the opposite of number B. Current X, so it's just as well opposite of that. Current X, now you are having current X is greater current X is greater than, the current A is greater, and then the current in Y is lower. So it's just the opposite of the first statement. Now you got to check to say what will make the brightness, the brightness. Remember, according to Ohm's law, we are saying V is directly proportional to I, which means that now the one now that is going to receive even more potential difference, it will depend on the current that is more. And then if we look at that will go with option number A. Now if you go to 1.6, you will see now we are talking to a parallel combination as well. To say in a parallel combination, already you know what happens in a parallel combination, but this question is about current, and we said current will be divided. So we're just going to look at how the current A1, you can see the A1 there, is going to be divided. We're going to look at how A1 will be divided. Don't forget, our current will flow. When it comes there, it will split. It will split there, other current will go that direction, another current will go in that direction. And then what happens, you are having A1. So we're saying, the statement number 1 is saying A1 is equals to A2 equals to A3. You know that this only applies in a series circuit where the current will remain the same. So it won't be the case because this is a parallel combination. The current does not remain the same. What remains the same is the potential difference. So number A cannot be correct. Now let's look at number B. We are saying A1 will be divided into A2 plus A3. That becomes the correct answer. So you know that resistors in parallel are current dividers, not potential dividers. They are current dividers. So I've emphasized that because that is the where our marks lie. Now, which one of the following produces the highest resistance? I think a question like this was there in one of your papers that you wrote. Which one of the following produces the highest resistance? And then if we look at, if you are having 2 ohm resistors that are connected in series, obviously you are going to add them. They will give you 4 ohm. But if you have, if you are having 1 ohm resistor for number A, if you are having 1 ohm resistors in series, it will give you 1 ohm plus 1 ohm. They are in series, 2 of them. So that will give you 2 ohm. That is for number A. Number A will give you total of 2 ohm. Number B, you are having 2 ohm resistors. So it will mean that you have 2 ohm and 2 ohm, and that gives you 4 ohm resistor. That's number B. Now, if you are having 3 ohms, 3 ohms resistors, it's 3 of them now, 3 ohms, but they are in what? They are in parallel. So they are in parallel. So you are having, in parallel, you are going to have your 1/3. According to the formula, you will say 1/R parallel is equals to 1/R1 plus 1/R2 and 1/R3. The more you have resistors connected in parallel, the less the total resistance. So this one will have the lowest resistance because of the parallel connection. These ones, there are two of them, but they are in what? They are in parallel. So still they will give you less resistance. So you know that when they are in parallel, the resistance is less. So C and D less, but for B and A, you can see that the highest will be for B because it's 2 ohms. So it's 2 ohm and 2 ohm. That gives you a 4 ohm resistor. So I hope the issue of R, V, and I, because this is what you are going to need now when we do structured questions. So it was very much important for us to be able to go through that so that you understand. Now we're saying which one of the following gives the correct combination of units for the quantity. Remember, you are having your energy there, and then when we talk about energy, we can talk about work done. We can talk about that is your energy as well. We can talk about current. When we talk about the current, remember your current is, by definition, is the rate of flow of charges. And then you are able to see that rate of flow of charges means that charge is measured in coulombs, time is measured in seconds. which is coulomb per second. So you're able to see that 1.8 will be number B, which is now your current. So you're able to choose that one. Which one of the following does not influence the resistance of a metal wire? It's important to understand factors that affect the resistance of a resistor. To say, does the shape affect the resistance of a resistor? Definitely no. But you can look at other options. The length does affect, the thickness affect, and the temperature affect. Remember from Ohm's law, we said the potential difference across the conductor is directly proportional to the current, provided that the temperature of the resistors remains there, the temperature remains the same. So it's important these three are correct, but number A does not influence the resistance of a conductor. Now let's look at the last two questions, which is now the maximum work done per charge. Remember what I said when I started the lesson. I said to you, if we look at our exam guideline, is defining a EMF, defining a EMF as the maximum energy provided by the cell per unit charge of a coulomb. So you can see that maximum energy provided by the cell, by the battery, is the maximum work done. Maximum work done, because we're saying what is potential difference is W over Q, which is work done per unit charge by a battery. But now the maximum, immediately when you say maximum, now we're talking about maximum energy provided by the cell per unit charge of a coulomb. We're referring to the EMF. So don't forget and enjoy how to define this EMF and be able to get it as the correct answer. It's number A. Now we're saying 1.11 there. The minimum resistance that can be acquired from the connection of two 4-ohm resistors. Remember, when you're having two 4-ohm, it's either you will connect them in series or you'll connect them in parallel. So that is the only way you're going to connect them. It's either you will have a series connection or a parallel connection. And for our series connection, if there are two 4-ohm resistors, you are having a 4-ohm resistor plus a 4-ohm resistor. Remember, you have to always write down the formula, because sometimes you can be excited and just when you say what is the calculate the resistance across the series connection, you just say 4 ohm plus 4 ohm. You are omitting that one mark for the formula. So it's important to always know that the resistance in series we are saying is R1 plus R2, which is equals to 4 plus 4, which is equals to 8 ohms. So the ones that they want the minimum, the lowest resistance that can be acquired. Minimum means lowest. That can be acquired from the connection of two 4-ohm resistors in series. So this is the maximum that we can get here. Now, if the two are connected in series, remember, for in parallel, we are saying 1 over R parallel is equal to 1 over R1 plus 1 over R2. And this is the equation that appears in your data sheet. However, you can as well always start by writing that formula, but now you can use the product over sum to say the resistance in parallel is equals to R1 product of R1 times R2 over R1 plus R2. So it's the product over sum. So you can use that only, it applies only when we have two resistors. So you can't do the product over sum for all of them like that. You can't say R1 times R2 times R3 divided by R1 plus R2 plus R3 when you are dealing with three resistors. No, it will apply when you have two. When you have more than two, I will even suggest that just go with the 1 over R parallel equation and use it. After that, you will take the inverse of your answer to get the R parallel. So it becomes easier when you deal with that way. Now you are able to say our R parallel is equals to product is 4 times 4, which is 16, if my math is still doing well. And then we have the sum, which is 4 plus 4, which gives you 8. So you have 16 over 8. That gives you 16 over 8 is 2 ohms. So you are able to get your answer and it's okay. Then that will be the minimum, will be 2 ohms there. You're able to choose your number B, and then you know because you have calculated. So what I'm emphasizing here is that as you are dealing with questions, ensure that when you choose an option, you are sure of it, you have calculated it. Because we are saying spend some time, at least 2 minutes, doing this multiple choice question each. 2 minutes, 2 minutes, 2 minutes, then you are able to solve them, you are able to be sure of the answer that you are choosing, and then you are able to collect maximum marks. Remember, in the exam, you have 20 marks that comes from these multiple choice questions, and we would like you to collect those marks. Now, let's look at this paper, which you wrote structured questions. They said a circuit diagram is set up in the diagram below, which is resistor R1, R2, and R3 are identical. So immediately when you say identical, you are saying they have the same resistance. They have the same resistance, okay? Now they are saying switches S1 and S2 are closed. So you can see, hence I indicated that the switch is either open or closed. There's nothing referred to as a switch. You will call it an open switch or a closed switch. So we have closed switches here, S1 and S2. They are both closed. According for this part of the question, remember, when we want to change the question, we can say we can open one of the switches, then the whole question now changes and the whole thing changes as well. So it's important that always you check as well. We are still talking now when S1 and S2 are closed. Whatever we are saying is dependent on the fact that S1 and S2 are closed. So those are the two things that we are looking at. Now, first question, state Ohm's law. So you can't go to write exam without knowing how to state Ohm's law, without knowing how to define EMF. So those you must be singing them by now. To say, we studied to say Ohm's law, the potential difference across the conductor. You can write it in symbol, you will write it in full to say the potential difference across the conductor is directly proportional to the current, provided that the temperature remains constant. Temperature remains constant. Please, no Ohm's law, no EMF, because those are two definitions that in most of our papers we are asking ourselves to write, to state them or to define EMF. So you must know how to do that. So you will say the potential difference across the conductor is directly proportional to the current, provided that the temperature remains constant. The temperature remains constant. Now, the question 9.2 was name the component of a non-ohmic conductor. Non-ohmic conductor in the diagram above. I think majority of you can't say component, you can't say L because we said name, so you must name it. So you remember when we started our lesson, we went through the components to say what do we call this, what do we call this, what do we call this. So you will know that is your bulb, that is given there. So you can't say L, you'll say it's a bulb. Remember your bulbs will quickly be hot and all that. Now write down the reading on the voltmeter with both switches closed on the voltmeter V when both switches are closed. Remember, the statement said ignore all internal resistance. It's very much important to always look at that statement to say, are we ignoring internal resistance or are we taking it into consideration? Remember what we said. We said EMF and V total potential difference are equal when the switch is, we said they are equal when there is no internal resistance. When no internal resistance, meaning that you have the EMF, which is the same as total potential difference. Now you will see that we are reading here the same what we are reading from there is the same what we are reading there for this one. So you can see that is parallel connection. Remember, when you say parallel connection, you are saying R1 plus L are in parallel with R2 plus R3. So you are saying these two are in series, and these R2 and R3, they are in series, but the two of these R1 plus L and R2 plus, they are all in parallel with one another, which means that if it's 12 volts here, it will read 12 volts here, because it's 12 volts for all that combination, and 12 volts because we said they are reading them from the same point. So we're saying that they will read the same 12 volts EMF of 12, a potential difference of 12 volts. So you're able to look at that and say, okay, it's 12 volts. That was the voltmeter reading. Switch S2 is now open. You see now it changes the question now to say, okay, now this one is open. It's open, which means this circuit, this one now, is now incomplete or not in existence, because immediately when it's not complete, there won't be flow of charges. So the charges will just flow like that. And then remember, our charges start from here. Don't forget the journey that the charges take. To say our charges were coming like that. When they came there, they were expected to be split. But immediately when you open that switch, the charges are saying, oh, we have high resistance here now, we can't go there. They now go only that road. So you are able to see that, okay, now all the charges will go. What is the question? Write down the reading on the voltmeter V. Remember, the voltmeter V still reading the same 12 volts as the EMF. So the voltage will remain 12 volts for that equation. I hope you got that. I found this question very good for you to always look at it when you preparing yourself to do even much difficult or much challenging questions, because they're not necessarily difficult, they're just challenging. And then we'll be doing another question as we speak, which includes internal resistance, and hoping that you will even gain even much confidence in dealing with this type of questions, and you will get as many marks as you can when it comes to electricity. Now we are saying switch S2 is closed. So you can see switch S2 is closed. Switch S2 is closed. And switch S1 is open. So let's see the dynamics. That one open, that one closed. Write down the reading on the voltmeter V. So you can see that when we open now switch S1, we are saying now we have EMF here. We are reading EMF here, but we don't have EMF across that circuit. So the EMF is 12, but now the switch is incomplete, so we only refer to the EMF that we are having there. We don't talk to the potential difference, so there won't be potential difference V that we are supposed to answer for that particular question. Now switch S2 is open. How will this affect still when S2 is open now for 9.6? S2 is open. We're saying how will that affect the ammeter reading? Right, only increases, decreases, or stays the same. This one is, I find it very important. Remember, we said when we have resistors in parallel, the total resistance decreases. But now, when we open this switch, we are removing the parallel connection, which means the total resistance will increase, because it will now be R2 plus R3 as our total resistance. And if you look at the relationship, you will know that our R is V over I. Then obviously now we are saying how will this affect the ammeter reading? What are we doing? We're increasing that one, which will decrease that one. So that will be decreases. It will decrease. And then both switches are closed. Resistor R1 is removed. So we're removing only this one. Resistor R1 is removed. How will this affect the voltmeter reading? Will the voltmeter reading increase, decrease, or remain the same? Remember what is happening. Still, this L will be a resistor now that is reading here. It will read the 12 volts for that light bulbs. And the R2 plus R3, they will read the same 12 volts there. So the voltage now is remaining, is staying the same there. So that will be your answer to that particular question. Now, before we deal with the structured question that includes internal resistance, always we're reminding you that always remember that when you talk about data sheet, that is the data sheet for electricity, and then you will know that for series circuits we're using that, for parallel that's what we are using, and the Ohm's law, R equals to V over I, then we are having for the power to be able to know that we have difference that we can use. For the current, I've talked a lot about this one, to say I equals to Q over T, which is taken from the rate flow of charges. So if you're saying define current, you know EMF, remember what we said, is the maximum energy provided by the cell per unit charge of a coulomb. So please always remember that here is just that it is what maximum. Look at this one, that is the V equals to W over Q. So you must be able to see these equations when you're asked to define, for example, potential difference. You will come to that and say, oh, is the work done per unit charge of a coulomb, or is the energy required or energy transferred to move a charge from one point to another. So you are able to look at that and be able to do your definitions. You have your energy there as your work done, which is VI delta T, I squared R delta T, V squared delta T over R. So all these equations, they're important, more especially when now we're going to deal with questions that includes power, because you must be able to do questions that includes power, and then with no wasting of time, we'll be able to move to such question. Let's look at this activity. I'm calling it activity 8. Look at it. It says a battery with an internal resistance. Remember, all the time we're just saying internal resistance is not there. Now it is there. We are saying a battery with internal resistance. You can see our battery there. The internal resistance is 1 ohm. So already, what does that mean? It means not the EMF and if I was to read the V across all those parallel combination there, if I was to read the V there, it won't be equals to EMF. Because now we are saying before, when the journey starts, because we are having resistance internally, we are going to leave some V. I don't like to use the word V lost, because it's referring to energy, and energy cannot be created nor be destroyed, but can be transformed from one form to another. I prefer rather to say V internal, to say we're going to have V internal. The presence of internal resistance brings us to the issue of V internal. So we know what we must understand is that V internal equals to IR. So we have that situation immediately when you say there is internal resistance, we're saying we have V internal, meaning that the EMF is going to be divided into V internal. So before we leave something which is V internal plus V external. So the external won't be equal, will be less than EMF. It's no longer equal. But when we say internal resistance is negligible, we're saying now you can say there is no R. When there is no R, E equals to total voltage of the cell. So it's important that we always have that in our mind. Now, we've agreed that our charge always flow from positive to negative. So we know that now we are having the EMF, which is the electromotive force. Remember, this is a force, electromotive force, which is the force for the motion of electrons, which are our charges here. So we're saying we are having a force that is going to make these charges to move. So the charges are going to move. The switch is closed. When the switch is closed, the charges will move. Definitely, this is the road that the charges will be moving with. And the unfortunate part about this question, we are not given how much is the EMF. So we don't know how much force that is pushing these charges as we go. But we know that we have a force that is pushing the charges to move. So that is our electromotive force. That is the force. Remember, when it's still here we are reading the EMF, which is the entire of it. But immediately when we leave this internal circuit, now we're moving, we now talk to the potential difference, which is our V, which is our V external. So you can see we have V internal here, we have V external that goes out now to push our charges. They are moving with the V internal, they come there. Good. Immediately when we reach that point, we know. So it's important that now we apply all that we talked of to say, as the charges flow, when they reach a parallel combination, what is going to happen is that they must split. Current must be split. They are at that crossroad now to say, at this crossroad, we have no choice. We must split because these are in parallel. This was a very interesting question, because now you can see that you have R that is in parallel with all this which you see here. They are in parallel with R. So now it's very much important that if now you want to know about the R, you must first get the R of all of this, and that will be in parallel with this R there. So it's very much important for our understanding of what is happening. Now, with the information that we are having, we just know that we are moving with V external, then we come there will be split of the charges, and then it goes like that. But look at that, always in questions you will have a key for the question. This is the key. Always look for that key. They will always, as long as you are having many unknowns, there must be a key that will help you to solve that problem. Remember, there are three variables that we are worried about. Our variables is R equals to is V, R, V, and I. Those are the three variables that are in our mind. But now our problem has been at least a little bit increased, because now we've included another variable which is small r. So we now have, instead of having 4 variables, we now have 5 variables, which is now we are having the EMF, because we're told that we have the EMF, we are having the current, we are having R external and R internal. And you know that if we have that, it means we are having V external plus V internal. So those are the variables that we are having now that we have to deal with as far as this question is concerned. Now, they are saying when with switch S closed, so we close the switch S, the current passing through the 8 ohm resistor. So you look for the 8 ohm, they are saying here. So now, what we know about 8 ohm, we know its resistance is 8 ohms. So it's R, we know it's R. Do you know its V? We don't know the V. Do you know its I? Yes, we are given I. So the key, always you'll have 2 variables that you will be given they will be known. You'll have 2 variables that you know. You have to find the third one. That is your key to the entire question. So your key to solve this problem will always now be to ensure that this 0.5 amperes around the 8 ohm, it is your key for this question. How so? So what you're going to do, you're going to say, okay, for 8 ohm, I know R equals to V over I. You know that R equals to V over I. If I can use this space, R equals to V over I. You know across that. You know the R is 8. You know that V, you don't know V, but you know that current is 0.5. So immediately when you have 2 known variables, you calculate the third one, and then that will help you in solving the entire problems that we are having. Now you will see that your V across 8 ohm resistor will be 8 times half, which is 4 volts. So you will use the calculator to say 8 times 0.5 will give you 4 volts. Already, now you know that this one is 4 volts. And if you know the voltage of this one, you know the voltage of this one, because the voltage of the other R, they are in parallel, the voltage must remain the same. You see those skills we're doing now, we are applying them to solve this problem. So immediately when you get the 4 volts there, you know that this 16 ohm resistor will have a voltage of 4 volts as well. So you know, and you know, now you have 2 variables across the 16 ohm resistor that you know the R, you know the R, you know the V, you don't know the I. So you can calculate I. You can simply say R is 16 equals to V is 4 over I. Maybe you're asking yourself to say, which question are we asking, are we responding to? That's what I'm talking to. Deal with the circuit diagram, and then you will get all the answers that you need. When you go to the questions, I'm telling you, you'll just be looking at the question and enjoying yourself. Now, what happens now is that you are going to have 16I equals to 4. You divide 4 by 16. Then you will get I equals to, I think my math is still correct, 4 over 16 is the same as 1 over 4, which is 0.75. So this will be 0.575 amperes. So you know that for 8 ohm is 0.5 amperes. For 16 ohm is 0.75. And remember, we said at this point, they're going to meet and add up again. So you can see that already you got your A1 now, because your A1 will be 0.5 plus 0.75, which will give you 1.25 amperes. And then you know A1. You see now, you are solving this problem small piece by piece by piece by piece, but already you are going there. You are getting it correct, because if you know this is 1.25 amperes, you can now be able to say, okay, 1.25 amperes R, remember the whole 1 comma, because this one is in series. So you know that the current remains the same, which is 1,25 here. You know that R V over I, always you're moving with that equation. How many variables do we know across 20 now? We know 3 variables. So what is our variables? It's our R, which is 20, equals to V, which is unknown, and I is 1,25. What did I say? I say this is 0,25. Just my bad there. I said 4 divided by 16 is 0,25, which gives us 0,25 plus 0,5. That gives us 0,75. Sorry for my math there. Always when you are solving these problems, go back and look so that you don't make mistakes and be able to lose marks. So we are saying we have 0,25 plus 0,5. That gives us 0,75 times 20, 0,75. Yeah, 0,75 as the I there, and the total I. V would be 20 times 0,75, and 75% of 20, that will give you 15 volts. So you're able to get 15 volts there. Then you know that, okay, this one is 15 volts. You know these ones are giving you 4 volts. When you add 15 and 14, they give you 19 volts. Look at the beauty of science. So you know the voltage across all these big parallel combination is 19 volts. And then because they are in parallel with this R here, it means the voltage here will be 19 volts, because the voltage across the parallel combination remains the same. Look at the beauty of all that knowledge that we were doing when we started with the lesson. Now you are applying it to say, okay, these two, they're in parallel, they will have the same voltage, but the whole of this, which is now 19 volts, will be having the same potential difference as this one, which is 19 volts, because they are in what? They are in parallel. So you're able to see that we have a 19 volts and another 19 volts. Now, if we go to questions, I mean, almost half of our problems have been solved. We've solved a lot of stuff here because we're able to see now that we are having our 0,75. That is the one that was flowing there. Then we know that is 0,75. The total current that went there was 0,75. So you are able now to do as many questions as possible. Look at that one. Let's look at 8.1. They said state Ohm's law. The first question was state Ohm's law, and I've overemphasized that to say it is the potential difference across the conductors is directly proportional to the current, provided the temperature remain constant. Don't forget, we're saying this happens when the temperature remains constant. So you have heard me, I emphasize the EMF definition and the Ohm's law to say these ones you must sing them like a song, because they are most likely to be asked in your exam. Calculate the reading on the ammeter A1. We just did that because we added the 0, that one and the other one. Then you're able to get your answer with no problem. Now, if you check, you will see that question 8.2 said calculate the reading on the ammeter A1. So you said it's 0,75 because you added the 2, they give you A1 there. Now let's look at 8.3 for 5 marks. So this one is the question. It's the question that makes this question to be a right question. So now you are given power here to say power is 12 watts. Power is 12 watts. Calculate the reading A2. So what we want current of A2. So that is for 5 marks. So I'll just take a small 2 minutes break because I know you will do this one very fast, and then I'll come back. Then we are able to answer how will you calculate that. Remember, I have given you the data sheet. Go to the data sheet and identify the right formula that you are going to utilize to answer this question. Then when I come back, then we are done. Then you are able to check the solution. Thank you. Thank you very much. I hope you were able to deal with this question, and then you are able to answer now as we are about to do. And I'm expecting that you got the correct answer. I know that my diagram has a lot of stuff, but I hope it helps you as well as you were trying to answer the question. Now, I think you might have seen that there is a formula out of the formulas that we gave you. Remember, we gave you the formulas for all the formulas there for power, where we have power. You check. This is how you choose. This is how you choose your correct formula. The first thing that you must ask yourself is that power is given. We're given power, but we were not given the work done or energy transferred. This was not given, and then we were not given the time. So you cannot choose equation number one. Remember what we are saying. We are saying we choose the correct formula, we substitute, we get the answer with correct SI unit. But when we talk about electricity, we're talking about vectors here mostly. So we don't have to worry with direction. Now let's look at equation number 2 there. You have power. Is power given? Yes, they gave us power. They said it's 12 watts. Did we manage to calculate the potential difference across R? You will have remembered that we said 19 volts. So you will know that we have 19 I. So all that we have to do is to go to write the formula, substitute, and then you are able to get the answer. Maybe you're asking yourself, why now will this have 5 marks? Remember already I've shown you how to do the question, but in answering this question, you will have first what you will have done first, you will have first used the 0.75 amperes that you got there. So you would have said, okay, I know that R equals to V over I is what we've done here. R equals to V over I. You write the formula, you substitute the resistance, which is 20, and then you write the 0.75, which is our current. And then when you multiply the two, they will give you your 15 volts for that one. And remember what we said. We said, okay, 15 for this and 4 for that. When you add those two, they give you the 19 volts. So the 3 marks, first 3 marks, obviously, you will have to find the 19 volts. And after finding the 19 volts, you go to choose the power equation, which is so P equals to VI. And they said power is 12 watts across that one, is 12 watts. And V, we got it is 19, so it's 19I. All you have to do is to divide both sides by 19. And if you divide 12 by 19, and then that by 19, you will get your I, which is your current, which will be your 0.63 amperes. So once you get your current is 0.63 amperes, then you were able as well to answer the question. A2 is 0.63 amperes. So at least you were able to move to that question. Calculate the reading on the voltmeter when the switch S is open. This is very technical. I want you to look at that. What matters here is the technicality of how the question is being asked. The question is saying calculate the reading on the voltmeter V when the switch is now open. We are saying EMF. Remember the voltmeter that we have when this switch S is open, we have EMF. So the question is saying calculate EMF, but the question didn't tell you straight or directly that calculate EMF. So it's very much important that you have that in your mind as you deal with this type of question, so that you don't have a problem. Remember what we said. We said our EMF is V external plus V internal, and already we knew that our V external here, we said it's 19 volts. We've agreed, me and you, that we have 19 volts. So all we have to do is calculate IR, which is to get the R, the small r, which you said is 1 ohm. So IR will be 19 plus, let's not write the SI units when we're calculating. 19 plus IR, our current was 0.63 plus, remember it's the total current. We must add 0.63 and add it was 0.75. I bet there. So you add your you add your 0.75 as your current that was flowing. So when you add 0.75 plus 0.63, when you multiply that by R, which is 1, then you are able to calculate your EMF. And if your calculator serves you well, you'll be able to say 19 plus that. I think it will give you 20.38. Yes, I've done 20.38 volts. I've done it here, 20.38. Then you were able to answer the question that says calculate the reading on the voltmeter when the switch S is open. So I think this question opened your eyes to say we won't at all times say calculate EMF. We can ask the same question but putting different ways. I am hoping that you have enjoyed this lesson, and then you were able to follow whatever that we were doing as the memorandum indicates there, which is all that we have been doing. And then you can see that that's what we did until we calculated our EMF, which we got 20.38. I'm hoping you are more positive with electricity and you will take many question papers and begin now to practice electricity as much as possible so that you are able to collect as many marks as possible. And then I would always like to end with this quote from Albert Einstein: anyone who has never made a mistake has never tried anything new. I'm saying with this closing that practice makes perfect. Continue to make mistakes as you learn. As long as you are not making mistakes in the final exam, make mistakes, ask your fellow learners, ask your educators to help you. And then Einstein said, the only way to learn is by you making mistakes. So continue to make those mistakes so that you can have a brighter future. And ask when you don't understand something, ask and you'll be able to get help. Till we meet again, thank you very much.